Estimating antenna capacitance can be accomplished through several methods. Here are two methods to determine the capacitance of a 2-meter monopole antenna without specialized test equipment. The first method involves physical measurements. Firstly, cut a piece of copper wire or rod to the desired antenna length, which is 2 meters in this case. Secondly, use a ruler or measuring tape to accurately measure the length, denoted as L, in meters. Thirdly, calculate the antenna radius, denoted as R, in meters. For a thin wire, assume a radius of approximately 0.1 meters. Fourthly, use the formula C equals 2 times pi times epsilon naught times L divided by the natural logarithm of 2 times L divided by R to approximate the capacitance, denoted as C, in farads. In this formula, epsilon naught represents the vacuum permittivity, which is approximately 8.854 times 10 to the power of negative 12 farads per meter. The second method involves resonance frequency determination. Firstly, connect the antenna element to an adjustable inductor. A variable capacitor could also be used. Secondly, connect the inductor to a signal generator or radio receiver. Thirdly, tune the inductor until the resonant frequency, denoted as F in Hertz, is found. Fourthly, use the formula C equals 1 divided by the quantity of 4 times pi squared times F squared times L to calculate the antenna capacitance, denoted as C in farads. It's important to note that these methods provide approximate values for the antenna capacitance. For greater accuracy, simulation software such as numerical electromagnetics Core 2 or Antenna Magus can be utilized. Additionally, the capacitance of the antenna will be affected by the surrounding environment, such as the presence of nearby objects or the ground. When constructing an antenna, the capacitance is a crucial parameter that affects its performance, especially at lower frequencies like the Schumann resonance frequency of approximately 7.8 Hz. Understanding how to estimate this capacitance is essential for designing an effective antenna system. The physical measurements method relies on the geometry of the antenna. The formula used is derived from the capacitance of a cylindrical conductor in free space. The accuracy of this method depends on the precision of the measurements and the assumption of a uniform charge distribution along the antenna. The resonance frequency method, on the other hand, utilizes the relationship between inductance, capacitance, and resonant frequency in an LC circuit. When the antenna is connected to an inductor, the combination forms a resonant circuit. By adjusting the inductance until the circuit resonates at a specific frequency, the capacitance can be calculated. This method requires a signal generator or radio receiver to detect the resonant frequency. It's important to consider the limitations of these methods. Firstly, the physical measurements method assumes that the antenna is in free space, which is rarely the case in practical situations. Nearby objects and the ground can significantly affect the antenna's capacitance. Secondly, the resonance frequency method requires careful tuning of the inductor to accurately determine the resonant frequency. Any errors in frequency measurement will affect the calculated capacitance. To improve the accuracy of these methods, several steps can be taken. Firstly, ensure that the antenna is placed in an environment that minimizes the influence of nearby objects. Secondly, use precise measuring tools to determine the antenna's dimensions and the resonant frequency. Thirdly, consider using more sophisticated simulation software to model the antenna and its environment. When designing an antenna for Schumann resonance, the goal is to achieve resonance at approximately 7.8 Hz. This requires a very large inductance or capacitance value. Since it is impractical to build an antenna that is kilometers long, an inductor is typically used to electrically lengthen the antenna. The inductor effectively increases the antenna's electrical length, allowing it to resonate at a lower frequency. The choice of inductor value depends on the antenna's capacitance and the desired resonant frequency. The formula for resonant frequency is F equals 1 divided by 2 times pi times the square root of L times C, where F is the resonant frequency, L is the inductance, and C is the capacitance. By rearranging this formula, the required inductance can be calculated as L equals 1 divided by the quantity of 4 times pi squared times F squared times C, in addition to capacitance and inductance, Other factors that affect antenna performance include the antenna's radiation resistance, efficiency, and bandwidth. The radiation resistance represents the power radiated by the antenna, while the efficiency represents the ratio of radiated power to input power. The bandwidth represents the range of frequencies over which the antenna performs acceptably. When designing an antenna for Schumann resonance, it is important to consider these factors to achieve optimal performance. The antenna should be designed to maximize radiation resistance, efficiency, and bandwidth. It's also important to consider the antenna's impedance matching to the receiver. The antenna's impedance should be matched to the receiver's input impedance to minimize signal reflections and maximize power transfer. Impedance matching can be achieved using various techniques, such as using a matching network or adjusting the antenna's dimensions. In summary, estimating antenna capacitance is a crucial step in designing an antenna for Schumann resonance. The physical measurements method and the resonance frequency method provide approximate values for the antenna capacitance. For greater accuracy, simulation software can be used. It's important to consider the limitations of these methods and take steps to improve their accuracy. In addition to capacitance, other factors that affect antenna performance include inductance, radiation resistance, efficiency, bandwidth, and impedance matching. By carefully considering these factors, an effective antenna system for Schumann resonance can be designed. The understanding of antenna capacitance, particularly in the context of low-frequency applications such as Schumann resonance, requires a deeper dive into the underlying principles of electromagnetics and circuit theory. The capacitance of an antenna is not merely a physical property but is also influenced by its interaction with the surrounding electromagnetic field. The methods described earlier offer practical estimations but are simplifications of a more complex reality. Firstly, let's delve into the concept of antenna capacitance from an electromagnetic perspective. An antenna, when viewed as a conductor in space, accumulates electric charge when a voltage is applied. This charge accumulation is analogous to a capacitor, and the ability of the antenna to store charge at a given voltage defines its capacitance. The capacitance is influenced by the antenna's geometry, its proximity to other objects, and the dielectric properties of the surrounding medium. Secondly, the formula C equals 2 times pi times epsilon naught times L divided by the natural logarithm of 2 times L divided by R, used in the physical measurements method, is derived from the capacitance of a long, thin cylindrical conductor in free space. This formula assumes a uniform charge distribution along the antenna and neglects end effects, which can introduce errors, especially for shorter antennas. Thirdly, the method based on resonance frequency provides an alternative approach to estimating antenna capacitance. When an antenna is connected to an inductor, it forms a resonant circuit. At the resonant frequency, the inductive reactance equals the capacitive reactance, and the circuit exhibits maximum impedance. By measuring the resonant frequency and knowing the inductance value, the capacitance can be calculated using the formula C equals 1 divided by the quantity of 4 times pi squared times f squared times L. Fourthly, it is crucial to understand the limitations of these methods. The accuracy of the physical measurements method is limited by the assumption of free space and the neglect of end effects. The accuracy of the resonance frequency method is limited by the precision of the frequency and inductance measurements. In practice, the antenna's capacitance can be significantly affected by its environment, including the presence of the ground, nearby objects, and atmospheric conditions. Fifthly, for more accurate determination of antenna capacitance, electromagnetic simulation software such as numerical electromagnetics code 2 or method of moments-based solvers can be used. These tools allow for detailed modeling of the antenna and its environment, taking into account factors such as ground conductivity, dielectric properties, and the presence of nearby objects. Sixthly, in the context of Schumann resonance, which occurs at extremely low frequencies, the antenna's capacitance plays a critical role in determining its resonant frequency. Schumann resonances are global electromagnetic resonances excited by lightning discharges in the cavity formed by the Earth's surface and the ionosphere. The fundamental mode of Schumann resonance occurs at approximately 7.8 Hz, with high modes at approximately 14.1, 20.3, 26.4, and 32.5 Hz. Seventhly, to effectively receive Schumann resonance signals, an antenna must be designed to resonate at these low frequencies. This typically involves using a large inductor to compensate for the antenna's relatively small capacitance. The inductor effectively increases the antenna's electrical length, allowing it to resonate at the desired frequency. Eighthly, the design of an antenna for Schumann resonance requires careful consideration of several factors, including the antenna's capacitance, inductance, radiation resistance, efficiency, and impedance matching. The antenna should be designed to maximize signal reception while minimizing noise and interference. Ninthly, various antenna types can be used for Schumann resonance reception, including loop antennas, dipole antennas, and monopole antennas. Loop antennas are particularly well suited for receiving magnetic fields, while dipole and monopole antennas are better suited for receiving electric fields. The choice of antenna type depends on the specific application and the characteristics of the surrounding environment. Tenthly, the radiation resistance of an antenna is a measure of its ability to radiate electromagnetic energy. A high radiation resistance indicates a more efficient antenna. The radiation resistance depends on the antenna's geometry and its proximity to other objects. 11thly, the efficiency of an antenna is the ratio of radiated power to input power. An efficient antenna radiates most of the input power, while an inefficient antenna dissipates a significant portion of the input power as heat. The efficiency depends on the antenna's design and the materials used in its construction. 12thly, impedance matching is the process of matching the antenna's impedance to the impedance of the receiver. This ensures maximum power transfer from the antenna to the receiver. Impedance matching can be achieved using various techniques, such as using a matching network or adjusting the antenna's dimensions. 13thly, in addition to the antenna itself, the receiving system for Schumann resonance signals typically includes a low-noise amplifier, a filter, and a data acquisition system. The low-noise amplifier amplifies the weak Schumann resonance signals, while the filter removes unwanted noise and interference. The data acquisition system records and analyzes the received signals. 14thly, the analysis of Schumann resonance signals can provide valuable information about the Earth's atmosphere and ionosphere. For example, the frequency and amplitude of Schumann resonance modes can be used to estimate lightning activity, atmospheric temperature, and ionospheric density. 15thly, Schumann resonance signals can also be used for various applications such as weather forecasting, earthquake prediction, and space weather monitoring. However, the use of Schumann resonance signals for these applications is still in the early stages of development. 16thly, the study of antenna capacitance and Schumann resonance requires a multidisciplinary approach, combining knowledge of electromagnetics, circuit theory, atmospheric physics, and signal processing. This field offers exciting opportunities for research and development, with the potential to improve our understanding of the Earth's environment and develop new technologies for weather forecasting, earthquake prediction, and space weather monitoring. 17thly, the design considerations for a 2-meter monopole antenna intended for receiving Schumann resonances present unique challenges due to the extremely low frequencies involved. A 2-meter monopole is significantly shorter than the wavelength of a 7.8 Hz signal, which is approximately 38,000 kilometers. This means that the antenna will have a very small radiation resistance and a large capacitive reactance. 18thly, to compensate for the antenna's small size and large capacitive reactance, a large inductor is typically used to resonate the antenna at the desired frequency. The inductor effectively increases the antenna's electrical length, allowing it to resonate at a lower frequency. The choice of inductor value depends on the antenna's capacitance and the desired resonant frequency. 19thly, the antenna's capacitance can be estimated using the methods described earlier, but it is important to consider the effects of the surrounding environment, such as the ground and nearby objects. The ground can significantly affect the antenna's capacitance and radiation resistance, so it is important to choose a location that minimizes these effects. 20thly, the antenna's radiation resistance is typically very small at these low frequencies, which means that the antenna will radiate very little power. This can be compensated for by using a low noise amplifier to amplify the weak received signals. 21stly, the antenna's impedance must be matched to the receiver's impedance to maximize power transfer. This can be achieved using a matching network, which typically consists of inductors and capacitors. The matching network transforms the antenna's impedance to match the receiver's impedance. 22ndly, the receiving system should also include a filter to remove unwanted noise and interference. The filter should be designed to pass the desired Schumann resonance frequencies while rejecting other frequencies. 23rdly, the performance of the antenna system can be evaluated by measuring its signal-to-noise ratio. The signal-to-noise ratio is a measure of the strength of the desired signal relative to the strength of the background noise. A higher signal-to-noise ratio indicates better performance. 24thly, the design and construction of an antenna system for receiving Schumann resonances is a challenging but rewarding endeavor. It requires a thorough understanding of electromagnetics, circuit theory, and signal processing. However, the potential benefits of this technology, such as improved weather forecasting, earthquake prediction, and space weather monitoring, make it a worthwhile pursuit. 25thly, in conclusion, understanding and estimating antenna capacitance is crucial for various applications, especially in the realm of low-frequency signal reception like Schumann resonances. While simplified methods can provide initial approximations, accurate determination often necessitates sophisticated simulation tools and a deep understanding of electromagnetic principles and environmental factors. The ongoing research and development in this field promise to unlock further insights into our planet and its environment.